Uh, mm, I wonder. Well, hopefully it works. Okay. Um, okay. Last time we started listing the basic properties of Borel-Moore homology, and as far as I remember, it was property number 7. It was about a smooth vibration. So had morphism pi, or maybe was it p? I think it was p. P from x to y. A vibration with a smooth fiber. F, and also it was globally oriented. So then in this situation, we have the pullback morphism by upper star from ith homology of y to I minus I plus d, sorry, homology of x. So d is dimension of the fiber. And this is due to the fact that the pullback of the dualizing sheaf on y is the dualizing sheaf on x shifted to d in the positive direction. And conversely, if I is a section of this bundle, then we have the pullback morphism with respect to this section. I upper star from ith homology of x to homology of y, and now the shift is in the opposite direction. And again, this is due to the fact that the pullback of the dualizing sheaf of x is the dualizing sheaf of y shifted now to the negative direction. Okay, and clearly, or at least hopefully, the composition of I and P is identity in the Borel-Moore homology of Y. Okay, and now some extra property. If both X and Y are smooth, then if we have subvarieties z inside y and z prime inside x, closed subvarieties, then let's assume additionally that the restriction of our projection to z prime is proper. Okay, and then necessarily, if we take the pre-image of Z and intersect it with Z prime, then its projection P again to Y is also proper. And its image is denoted as the composition Z composed with Z prime. Okay, so under all these conditions, for a class in the Borel-Moore homology of Z, so on Y, and another class C prime in Borel-Moore homology of Z prime. So in X, there is a projection formula. So the push forward of the pullback of C cap product with C prime is C cap product with the push forward of C prime. Okay, now let's go to property 8 and to the next page. In fact, maybe I can try to fit the next property onto this page. So the action of cohomology so there is a morphism from ith cohomology of X tensor jth homology of X into J minus ith homology of X, denoted just by dot product. And well, there are various ways to think about this multiplication. One way, again, is if you think of Borel-Moore homology as homology with coefficients in the dualizing sheaf, then the usual cohomology act on the cohomology with arbitrary coefficients, for example, with coefficients in the dualizing sheaf. So that there is this action. Okay. So now the next property 9. It is the Thom isomorphism. And we have an oriented vector bundle. V project to X. So this is pi. And we also have the zero section. This. And then we have the Euler class. Maybe let's note by E, E of V, and this is the class in cohomology. So here R is the rank of V, and we studied this in the basic topology course maybe 2 years ago or something like this. So let me not go over it again. Okay, so then we have the morphisms between Borel-Moore homology. Okay, so this is the pullback with respect to zero section and the pullback with respect to projection. And for any class in the Borel-Moore homology of the base, if we go there and back with respect to the zero section, push forward and pull back, then this is just the multiplication of the Euler class by the Euler class of this vector bundle, and now if X is a closed smooth subvariety in a smooth variety Y, so an a closed embedding like this, then again for any class in the Borel-Moore homology of X, the composition we go to Y and then go back to X is the multiplication by the Euler class of the normal bundle, because locally it's the local question, and locally the tubular neighborhood of X and Y looks like the normal bundle. Okay, so now we're all, oops, sorry. The last basic property is the so-called excess intersection. So we have two smooth subvarieties, Z1 and Z2, oriented in an oriented manifold M, and we assume that the intersection is smooth but not transversal. And the intersection is so-called clean, but not necessarily transversal. What does it mean? It means that the well, let's define, say, T1, 2. It is the normal bundle to the intersection, say Z, the intersection, modulo the sum, the normal bundle to one thing plus normal bundle to another thing. Yeah, there is a problem to distinguish between Z and 2. I'm sorry. Okay, and now the clean intersection means that that the intersection of the tangent spaces at any point to Z1 and sorry to Z2 is the normal tangent bundle to their intersection. Okay, at any point Z in the intersection. Okay, but for example, by not transversal intersection, I mean that they can coincide. Z1 can coincide with Z2. Yeah, the intersection will be again smooth. It'll be the same as Z1 and Z2, and this this condition of cleanness will be clearly satisfied, but it will be not transversal intersection. But what we have in this situation is that if we take the fundamental class of one subvariety and take its cap product with the fundamental class of the other one, in the Borel-Moore homology of the ambient variety M, then what we get is the Euler class of this vector bundle T1, 2, acting on the fundamental class of their intersection Z. Okay, so this was the last basic property, now finally I'm able to define the convolution. In the Borel-Moore homology. Okay, so we have three connected and smooth oriented varieties, M1, M2, and M3. So they are all connected, smooth and oriented manifolds. And we have closed subvarieties, but not necessarily smooth anymore. Z1, 2 in the product of M1 and M2, and Z2, 3 in the product of M2 and M3. Then we can associate to this their composition, so to say, or convolution in M1 times M3. So namely, these are all points M1, M3, such that there exists M2, such that M1 and M2 lies in Z1, 2, while M2 and M3 lies in Z2, 3. Okay, and now we assume that so let D be the dimension of M2, and we assume that the projection from the let's say it Z1, 2 times Z2, 3 intersected with the diagonal in M2. Yes, so when I multiply these two, I get in M1 times M2 times M2 times M3, yeah? And now I intersect with the diagonal over M2. And I assume that the projection from this to M1 times M3 is proper. Okay, so under this assumption, I have the convolution morphism from HI Borel-Moore homology of Z1, 2 times jth Borel-Moore homology of Z to 3, 2 hi plus j minus d Borel Borel-Moore homology of their composition Z1, 2, and Z2, 3. By the way, note that this proper morphism above has the image exactly the composition of Z1 and Z2, 3. And this convolution acts as C1, 2 controlled with C2, 3 by definition is the image of projection of P1, 3 over C1, 2 tensor, the fundamental class of M3, cap product with the fundamental class of M1 tensor C2, 3. Okay. Okay. So there we are. And this was some crash course on Borel-Moore homology. I listed all their basic properties and defined some convolution. And now we can recall the theorem we are in process of proving. So we had at element A, well, it was the pair semi-simple element of our group G, the product of semi-simple group and the multiplicity of group C star. And then this defined a central character of the affine Hecke algebra. So it gave rise to some central reduction. It was the order of W squared dimensional central reduction of our affine Hecke algebra. And the theorem was that this central reduction was isomorphic to the Borel-Moore homology of the Steinberg variety of triples, fixed points with respect to the action of this element A, and say with complex coefficient. With respect to the convolution, which I just have defined. So now let's well, comment on this theory. Proof, but modulo everything. So I mean, I will construct a chain of morphisms that will turn out to be algebra isomorphisms. Okay, so first of all, this centrally reduced affine Hecke algebra is isomorphic to the module over the center. Center is the representation ring of our group G. And here I have the equivariant K theory of the Steinberg variety of triples. And this is our basic theory that we proved the whole October, that we were in the process of proving the whole October, and finally proved last time. Okay, so this is the main geometric theory. Okay, now we will use it. so we will only use the affine Hecke algebra or its central reduction in this geometric incarnation. Okay, we will never ever again recall its generators and relations and its algebraic definition. Okay, now from this we go a little bit further. So this is the same central reduction, but over some smaller representation ring. Okay, so here A inside G is the Zariski closure of all the powers of this element A. Okay, so this is clearly a commutative algebraic group, and hence the neutral component A naught is a torus, but not necessarily one-dimensional. Yeah, if this element A is sort of irrational enough, wild enough, it can generate the whole Cartan torus. Yeah, if it for a general in the sense of Andrei V element of the Cartan torus, it will generate the whole torus. But still, there might be also a group of connected components. Yes, if this A has finite order, then certainly this group script will be disconnected finite algebraic group. But again, abelian and even cyclic. Okay. So what do we know about this? We know that this subgroup A is contained in some maximal torus inside our extended group, and well, this maximal torus is the product of Cartan torus and this extra C star, and we know that the equivariant K theory with respect to this torus of anything at all, so say of our variety of triples, but of any variety at all, is the representation ring of this torus tensor over the representation ring of our ambient group of the equivariant K theory with respect to this ambient group, and also the equivariant K theory with respect to this smaller abelian commutative algebraic subgroup is the representation ring of this commutative group tensor over the representation ring of torus with K theory of X, and this is all due to the fact that the K G of X is a free R of G module. And this in turn is due to the fact, well, to the cellular fibration limb. But everything splits into cells. And for a cell, the equivariant K theory is the same as for a point. And for a point, the equivariant K theory is just the representation ring. Okay, so this was an explanation of this upper equality here. Fine. So now we know this equality. Let's move on. Now we define. I don't know. We'll start here. Maybe let me start here. Morphism. RA. So this morphism goes from the specialized equivariant K-theory of the variety of triples to the specialized equivariant K-theory of the fixed point set. Okay? And this fixed point set with respect to the Zariski closure is clearly the same as the fixed point set with respect to this single element A. Okay, then you see on this fixed point set, the action of our group A script clearly is trivial. Okay, so when I take the equivariant K-theory of the fixed point set, I get just the equivariant K-theory for the point tensor, the K-theory not equivariant for the fixed point set. Yeah, because the action is trivial. Okay, and then when I tensor over representation ring, okay, when I tensor with this just one-dimensional module C sub A, I just get one-dimensional space. So it follows that C tensor this equivariant K-theory is just a non-equivariant K-theory of ZA, but maybe complexified. Okay, so all in all, we want to obtain a morphism RA here from the specialization of equivariant K-theory of the whole Z, the whole variety of triples, to the non-equivariant K-theory of the fixed point set. Okay, that's what we want to define, and I will define it on the next page. Okay, so let me rewrite once again. I want to have this morphism from the specialized equivariant K-theory of the whole variety of triples to the K-theory of the fixed point set. That's what I want to define, and it will be defined as a composition of a few morphisms. Namely, we start here. Then we take restriction. I will first write what I want, and then I will explain the meaning of these words. Okay, so I restrict to the fixed point sets, and at the first glance it makes no sense, right? Because the Steinberg variety of triples is something very singular, and its fixed point set is perhaps even more singular, and the restriction in the coherent K-theory makes no sense because there are infinitely many torus. So I will have to explain what I mean by this. And then I just go to non-equivariant K-theory. This I already explained that this is fine, just because there is no action of script A on the fixed point set. And finally, there is one more arrow, and this is one tensor, some Euler class inverse. So again, I will explain what do I mean by this, and it goes to the same place, but it is an isomorphism, and this is some correction factor. And again, I will explain what is this correction factor and why do I need this correction factor. So here, explanation. First of all, this I pullback is the restriction with supports in the ambient smooth variety. So what do I mean by this? By the very definition, this fixed point set in the Steinberg variety embeds into the ambient Steinberg variety. This in turn embeds into the square of cotangent bundle to the flag variety. Yes. Well, in fact, it is some. You may view it either as the union of conormal bundles to the orbits, diagonal orbits of G, or as the fiber product of this cotangent bundle to flag variety over the nilpotent cone viewed as a Springer resolution. And similarly, the fixed point set is embedded into the square of fixed points in this cotangent bundle. That is in turn embedded into the non-fixed points. Okay, and now this is smooth, and this is smooth because we take the fixed point of an automorphism of a smooth ambient algebraic variety. And now, if you still remember in our early days, we defined the K-theory of the Steinberg variety of triples in terms of this embedding. So we considered, let's say, resolutions by vector bundles on the square of flag variety, whose cohomology were supported in the Steinberg variety of triples. Yeah, this was one of the equivalent definitions of the K-theory of the Steinberg variety of triples. Okay, and the same works for this fixed point set, the A. Yeah, any coherent sheaf on this ZA has a resolution in terms of vector bundles on the ambient variety. This is the fixed point set of A in the square of cotangent bundle like variety. There's a resolution in terms of vector bundles whose support again lies in this non-smooth ZA. Okay, and now we just take restriction from the square of cotangent bundle of like variety to its a fixed point sets. This is the meaning of I upper star. Okay, this is the restriction in the ambient smooth variety. And that's called the restriction with supports in this subvariety n tilde a times n tilde a. Okay, so finally, this is defined. Now let's define the Euler class. And first we define some auxiliary Euler class like this. And this is just the usual definition. So we take the sum with signs of the exterior powers of the co-normal bundle to the fixed point set inside the cotangent bundle to flag variety. Okay, and this is an element in the equivariant K group of this fixed point set. And again, since the action of A on the fixed point set is trivial, this is nothing but the representation ring of A tensor, the non-equivariant K theory of the fixed point set. Okay, this is the usual definition of the Euler class. We already mentioned it a few times before. And then if, say, iota is an embedding from the fixed point set into the cotangent bundle of flag variety, then we know that the composition of iota push forward and iota pull back is the multiplication by this Euler class. Okay, and it's an in fact, it's an automorphism of the equivariant K theory of this. So it's an automorphism if you localize in the maximal ideal M A in the representation ring of this group. Okay. So we're almost done. Now we can define the desired Euler class. And this is the image of this previous Euler class, the big one, under composition. So we start with the equivariant K theory of the fixed point set, the smooth fixed point set. So we know that this is the product of the representation ring and non-equivariant K theory. And then we can take the evaluation at point A and identity along the second factor. So we go to just complex numbers and the non-equivariant K theory of the fixed point set. And this is but non-equivariant K theory complexified of the fixed point set. Okay, so this is the definition. But now let me write it more explicitly. Okay. So if we split the normal bundle, or maybe conormal bundle, to the fixed point set in the cotangent bundle of like variety, we split it into the characters, into some maybe eigen bundles with respect to the action of our group A. For the eigen characters of the commutative group A. Then this specialized Euler class is the tensor product over all those eigen characters of the sums negative nu of A to the power I, the exterior power of this conormal bundle. Okay, there we are. So now I have defined all the ingredients. Maybe let's go back. Yeah, we're defining this morphism RA at the very top of this page. It was the composition of those guys. So first was restriction with support. Then we just rewrote the specialized equivariant K-theory in terms of non-specialized sort of concentration theorem, Thomason. And then we had this extra correction factor along the second factor, right? But know that it's only along the second factor. And we are using the fact that this correction factor is invertible. And so we multiply with the inverse element. Yeah, it's, you see it here, it's Euler class inverse. That's what we do. And then the key statement about this is that this composition RA commutes with the convolution. So in other words, RA is a homomorphism of convolution algebras. Okay, and we will omit it. So I will not prove it, at least so far. It's again one of the basic properties of the equivariant K-theory, and well, hopefully we'll return to it at some point, maybe in our next life, but not now. Okay, so let's move on, and we're almost there. You see, we produced a homomorphism from HA to the non-equivariant K-theory of the fixed point set, like this. And we wanted a homomorphism to the Borel-Moore homology. So we are almost there. We only need a homomorphism from non-equivariant K-theory to the non-equivariant Borel-Moore homology. And well, probably you can guess what it is. It's the sort of Chern character. or rather some Riemann Rockmorphism. So to define this letter homomorphism, we use first of all the Chern character. From the K theory to Borel-Moore homology. And what is the meaning of this? Usually the Chern character goes from the vector bundle K theory to the cohomology, right? And here we use again the supports. So we have the A is embedded into n tilde A times n tilde A. And so the Borel-Moore, or I don't know, the K theory of the A is the K theory of this ambient smooth variety, but supported on the A. Okay, and similarly, the Borel-Moore homology of the A is the cohomology of the ambient smooth variety, but supported on the A. Okay, and then we use the standard Chern character from here to here, but the supports match, and so we obtain a Chern character, the desired Chern character from coherent K theory to Borel-Moore homology. Okay, and then also maybe let's say then also we have the Todd class. Of the smooth variety, then the 6-point set in the cotangent bundle to the flag variety, and this lies in the cohomology ring of. Oops, sorry. Let's forget what to do. Easy. Okay, and again, I think we defined this Todd class in our topology class a couple of years ago, so I will not even recall what it is. Some expression in terms of Chern classes of the tangent bundle. And now, finally, there is the bivariant Riemann Rockmorphism. And that's what we need. Riemann Roch from the K theory to Borel-Moore homology. And here the coherent sheaf goes to 1 along the first factor, and then the Todd class along the second factor. Okay, and you just cap it with the Chern character of F. Okay, and the second key claim is very similar, namely that this bivariant Riemann-Roch commutes with the convolutions in K-theory and in Barrel-Moore homology. And this is, at least it uses the full strength of the Riemann-Roch theory. So again, I will not prove it, at least right now, maybe sometimes in the following years, but it uses at least the usual Riemann-Roch theory, and also something else. It's stronger than the usual Riemann-Roch theory. Fine. So we will only use it as a black box, and at least the main theorem is proved now. So we had this long chain of where was it? Yeah, we wanted to construct this chain of isomorphisms, and we started with specialized K theory. Then we used this correction homomorphism to non-specialized K theory of a fixed point set, and from the K theory fixed point set, we went to Barrel-Moore homology of the fixed point set, and there we are. That's what we wanted. So I declare the main theorem proved at this point, and now let's use it. Essentially, again, from now on, we'll just use it as a black box. We will classify the irreducible representations of this convolution Barrel-Moore homology algebra. Okay. So we'll never again recall the algebraic definition of the affine Hecke algebra, or even the K theoretic realization. We will only use this Barrel-Moore homology algebra and nothing else. Just this. Okay. And for what we at least hope to do today, this transition from K theory to Barrel-Moore homology will be not very important. So I will proceed to define the so-called standard modules, and then co-standard modules, then the morphisms from standards to co-standards, like in category O that you all like. And the images will be irreducible representations, and this will be the complete classification, and also will be able to compute their characters. So this will be a tremendous success. And somehow at this stage of just definitions, we could still work with K theory if you don't want the new notions of Barrel-Moore homology. But to prove anything at all, you will desperately need Barrel-Moore homology. So it's it's more soft theory because of its sheaf nature. So that this will be clear. It will become clear next time. Today I will only define the standard constandard modules, but to work with them, you will need the sheaf theoretic analysis. Okay, so our next topic is the construction of the modules over this Barrel-Moore homology convolution algebra. And to this end, we'll use the Springer construction. So I have the Springer resolution map. Say mu from n tilde to n. So until the is the space of pairs Borel and the nilpotent element inside, and we just forget the Borel. And also inside we have the fixed point variety, and here too. So I will denote by mu the restriction to the fixed point subvarieties. And so recall now that A is a semi-simple element, an element in the group G and the extra element in the multiplicative group. And now the fixed point set in the nilpotent cone, just by the very definition, is the set of nilpotent elements, nilpotent cone, such that the adjoint action of this, sorry, it's not G, it's S. Adjoint action of S on X just multiplies it by T. Okay, just by the very definition. And the fixed point set upstairs in the cotangent bundle flag variety is very similarly Borel subalgebra, an element here, but both must be fixed. Okay, and this nilpotent element must be inside the Borel subalgebra. So now if we project this fixed point set to the flag variety, since X is fixed anyway, this projection identifies a Springer fiber with a subvariety in X, in the flag variety B. Namely, these are the fixed points of S and X. Okay, so somehow the status of S and X is a little bit different. S is a semi-simple element in the group, so it acts on the flag variety and has its own fixed point set, and it is smooth subvariety and flag variety. And X is not an element in the Lie group; it's an element in the Lie algebra, right? So when I say the fixed point sets of X in the Borel in the flag variety, then what do I mean by this? I mean that there is an action of our group G on the flag variety. So the Lie algebra of G acts by vector fields. In particular, this element X gives rise to a vector field on the flag variety. Now this vector field may vanish at some point. Okay, and this B sub X is the set of zeros of the corresponding vector field. Okay, so let me write it down, that Bx in B is the zero set of the vector field X in Lie G, okay, on this flag variety. And while Bs is necessarily smooth, this zero set of the vector field S, it's the usual Springer fiber, and it's usually very, very singular. Okay, so Bx is the usual Springer fiber, and typically very singular and reducible. Has many irreducible components, but they are all of the same dimension, so it's equidimensional, and the number of these irreducible components is good. It's the dimensional subrepresentation of the Weil group. There's a whole big theory about this. But anyway, B sub X is singular, but B upper S is smooth. And now we intersect them. So these are the varieties we will be concerned with for the rest of November at least. Okay. So just a remark is that this B Sx is non-empty since this B Sx is the fixed point set of a group generated by S and the exponents of the multiples of X. Okay, and since we know that the adjoint of S is the multiple, the adjoint action of S on X is some multiple of X, hence this group is solvable and hence contained in Borel B, and hence this particular Borel B does lie in the fixed point set we're studying. Okay, so now what else we can say? We can say that our convolution algebra of Borel-Moore homology of the fixed point set acts by convolutions. On the Borel-Moore homology of any particular Springer fiber. And this is the same as Borel-Moore homology of this fixed point set. Okay, and essentially this is it. This will give us the supply of representations. Just these homology of fibers will be our basic building blocks. But we just need slightly to decompose them. So say in case of GLN, if our group G is GLN or SLN, but maybe better GLN. If our group is GLN, then just that's it. We need nothing else. These are the standard modules, just as they are. But in general, we need slight decomposition. Namely, we have this simultaneous centralizer G of Sx, and this is the centralizer of S intersected with the centralizer of X, and this is some subgroup certainly of G, and C of Sx is its component group. So G of Sx modulo the neutral component. So it's just a finite group. And again, note that if G is GLN, then all those guys are trivial. Just because the centralizer is the set of matrices, invariable matrices that commute with something. right? But for matrices, commuting with something is a linear equation. So we have just a linear subspace in matrices intersected with some other linear subspace in matrices. Anyway, it's linear subspace in matrices. But our matrices have to be invertible. So then we have to remove the intersection of this linear subspace with the determinant equals 0 subvariety. But it's still connected, right? So for GL and the centralizer of anything is connected because it's the centralizer in matrices. By n is a vector space. And then we have to intersect with determinant is non-zero. So it's an open subspace, an open subvariety of a vector space. Okay, so for GLN, there is nothing to speak about, and in general, these groups might be pretty interesting. For example, if there is no semi-simple element, but just a nilpotent element, this group of components of centralizer of a nilpotent element in classical types, it's always a commutative group of order some power of 2, but in exceptional series, it may grow up to this symmetric group on 5 letters. So for E8, there is some very special nilpotent class whose nilpotent orbit, whose pi1 fundamental group is the symmetric group on 5 letters. Okay, and say for F4, it's symmetric group on 4 letters. And for G2, it's symmetric group on 3 letters. Yeah, I mean, it can happen for some very special nilpotent orbits in these groups. Okay, so now finally, the action of this component group Vx on the Borel-Moore homology of BSX. I mean, the whole group GSX acts there, right? But certainly the neutral component acts trivially on the Borel-Moore homology, on cohomology, on anything at all. The action of the neutral component, for topological reasons, is trivial. So only the component group survives. And it acts there, and just by the construction, it commutes with the action of the Borel-Moore homology of this variety of triples. And now let's give this formal definition. So if some irreducible representation of the component group occurs in this homology, I mean with non-zero multiplicity, then we say, or we write, that chi lies in the relevant part of this representation theory. So we say chi is relevant. I mean, not all the representations occur. and we set k a x chi is the multiplicity space so over the component group from this representation to the Borel-Moore homology of BSX. Okay, just the multiplicity space. And this is called the standard module, a standard module. Okay, I mean, since the action of the Borel-Moore convolution algebra commutes with the action of component group, certainly all the multiplicity spaces of the component group carry the residual action of this convolution algebra. Okay, and these are the standard models over the convolution algebra. Okay, just one more remark. That the Borel-Moore homology, what to say, in question, I mean, of everything we encounter here, live only in even degrees. And again, for GLN, one can prove this pretty elementarily. Namely, one can construct some paving by affine spaces, cellular decomposition of any Springer fibers. And this was done by Spaltenstein some, whatever, 50 years ago, or maybe, yeah, about 50 years ago. But for exceptional groups, it's very, very difficult. It was proved by Lustig and De Concini and Procesi, maybe like 30 years ago, but it's very, very difficult. So I mean, maybe even this fine paving is not known till nowadays, though it sounds very strange, but still I think it's not known that for Springer fibers in exceptional types, they have cellular decomposition. It is possible to prove that the odd cohomology and homology, they vanish, but there is no cellular decomposition known for exceptional types. It's something very strange. Okay, so now let me define the costandard modules. And to this end, I consider the centralizer of the semi-simple element, and we take its orbit through X, this nilpotent element, let us call it O, some nilpotent orbit, and it lies in the fixed point set. And let's take a local analytic slice. I mean, in the classical topology, yeah, not on algebraic, not on Zariski topology. Say, let's denote it by S to this orbit, and S tilde will be the preimage under this Springer resolution map of this slice. And then this is a smooth say tubular neighborhood of the Springer fiber. So BSX. And it is homotopy equivalent to the fiber itself, so it can be so this fiber BSX is a homotopy retract of this neighborhood. Okay, and okay, maybe let me make another remark. So if say S is just nothing, the identity element, and X is a subregular nilpotent element, so maybe remember that there is a unique open nilpotent orbit, and it's called it consists of regular nilpotent elements. But then there is also unique smaller orbit. So there are many nilpotent orbits, but there is one maximal, and there is just one submaximal. It has the dimension just two smaller. So unique submaximal nilpotent orbit. So say in type A for GLN, X is the big Jordan block plus or just one zero matrix like this. So it has type n minus 1, 1, the Jordan type like this. Okay, and say for SPN, the same type as SP. Yeah, for SPN, if n is even, then the same type works. But not for SON. Okay, so if this is so, then the Springer fiber is one-dimensional, so it's a curve, and but it is a singular curve. It's a union of projective lines. A union of projective lines. Intersecting according to some Dynkin graph. What do I mean by this? Say in type GLN, it will be so it will be type AN minus 1, and so you will have just one P1 intersect with another one, and so on with the last one. Okay, so the vertices are those components, and the edges are their intersections. Okay, so to this I write vertex here, vertex here, vertex here, vertex here, and vertex there. Okay, and say for SO8, this is D4, so I will have one central component, and it will intersect 3 other components. So the graph will be like this. And say for G2, I will have the same. But for the symplectic group that is folding of type A, I will have something unexpected for SP2N. I will rather have this, and then one more, and then two more. So I'll have the graph of type D unexpectedly. Okay, there is some strange whatever swapping here. So it's swapping of folding. Okay, so type C is obtained by folding of type A, type B is obtained by folding of type D, but the diagrams are vice versa. Okay, okay, so there we are, and unfortunately I have to stop in 2 minutes, but let me finish with this. This is the same, so it's equal to the special fiber of the resolution of the corresponding Kleinian singularity. Yes, I hope you have heard about these Kleinian singularities. So you take A2 modulo some finite group gamma. This gamma is a finite subgroup of SL2C, and they are again classified by Dynkin diagrams. So you take the corresponding Dynkin diagram. So say for type A, you take the cyclic group of corresponding order, and for type D, you take dihedral group. Okay, so the last words I want to pronounce is that this S tilde from the last page is this resolution itself. Okay, so we have the fiber inside this smooth thing, and the fiber is a homotopy retract of the ambient smooth thing. So this will be equal to some a tree of projective lines, and this will be equal to the resolution of A2 mod gamma like this. Okay, so if you ever encounter S tilde, you'd rather imagine this thing. Okay, that this is how it works, sort of in general. But certainly the singularity in general is much worse, and you cannot really describe it. But it's something like this. Okay, so that's all for today. I didn't even have time to define the costandard models, but they're essentially Borel-Moore homology of those smooth pre-images. So we'll do this next time. So now I'm saving my notes, and if there are no questions, I will stop our session and then stop the recording, God willing. Okay. So if there are no questions, I stop today's session. Thank you. Goodbye.
Thank you.